Hello, everyone. Good afternoon. Okay, so today we are going to be talking about other nonlinear methods, kind of moving beyond splines and kernels. Moving beyond splines and kernels. So as a quick refresher, right, splines are a semi-parametric approach that is functionally flexible, and kernels are a good, sort of powerful, non-parametric approach for finding decision boundaries. So to give some historical context, a lot of these approaches tend to have specific use cases depending on the types of data that you have, depending on the types of models that you're trying to fit. And I would say that both of these methods, while still in use today, really became sort of outshadowed in popularity relative to what we're going to talk about today. And a lot of we're kind of well beyond thinking about the folks who are still in developing methods and approaches for inference, and really kind of more solidly in the development of predictive models. So what really became popular are more traditional methods in machine learning. And so what we're going to be talking about are techniques that are, so in machine learning, similar in principle to approaches we have already discussed. But in practice, are powerful tools to handle scaling. And I think what really helped drive the popularity of some of the things that we'll talk about today, such as neural networks, are kind of a simultaneous improvement in computing capability, but also sort of the larger prevalence of, I guess, what you would call big data, not only in the sense of like having lots of data points, but also having lots of variables, or we're going to start using more kind of machine learning lingo. They call these explanatory variables features. So you have more features. So explanatory variables. And you have more data, larger and or more rows, essentially. And we'll talk a little bit about, and this is actually a subject that I think I've touched on in previous lectures, but about why some of the techniques are kind of better suited to handle this big data. Okay. So let's take a look at, we'll just jump right into it. Let's take a look at a example of a neural network. So neural network example that replicates a linear regression. And I will try and use notation that replicates a lot of commonly seen notation in, I guess, more common machine learning classes. And we'll try and equate them to what we've been doing. So we got I1, I2, that's a cursive L. And so we have some kind of function that is a function of my two eyes. Looks something like this. Oops. Okay. So these are arranged as tensors. These are my weights. And this is an output layer. And really, when I look at this, this is functionally equivalent to y equals beta 1 x1 plus beta 2 x2. These eyes are essentially my data inputs, but one of the differences is that these tensors can be arranged in multiple ways, and it kind of really follows the nomenclature that we talk about, or that we use in R. So if you have a scalar, this is a 0-dimensional tensor. A vector is a 1D tensor. A matrix is a 2-dimensional tensor, and then an array is an n-dimensional tensor. And this will allow us to be really flexible in the way we arrange the inputs into your network example. Because we can very easily, you can see here, operate in multiple dimensions. If, for example, we wanted to weight them with the same weight as you go out of your particular node. Okay, any questions about this so far? All right. So I actually like the fact that the notation for this set of models is, or for the neural networks is actually differentiated a little bit from your traditional linear regression, even in the simplified form. And I think one of the reasons for that is due to the fact that we're actually calculating your weights slightly differently from the way that you would calculate your betas. And what that means in a sort of practical applied sense is that you could get really slightly different answers when you get when you apply a neural network to calculate this equivalent linear model compared to calculating your betas from your OLS as you sort of traditionally do. So solving for betas versus W's. So I mentioned before, the math for an OLS is actually solved analytically. And as a quick refresher, I'm sure many of you guys have seen this before. If you've taken like any old regression class, right? So this is how you actually solve for the betas in a closed form solution. And because it's an analytical solution, we're guaranteed the correct solution. And this is very fast in theory. So weights are obtained by solving numerically through optimizers. Oops. So such as gradient descent, I think is one of the most common ones. Although even that is a generalization, there are a couple different forms of gradient descent that you could use. And the benefit of this is that it's not nearly as memory intensive. And that's one of the hallmarks of, so not nearly as memory intensive as analytical methods. And that's one of the hallmarks of this is that once you're dealing with really large data sets, you don't have to hold the inverse matrix in memory, which can be very large from a memory standpoint. Scales very efficiently. And importantly, can be applied flexibly to any functional form. So what that means is that this particular linear equation is only really specific to your ordinary least squares calculation of your beta parameters. Okay, this like, you couldn't use this equation to solve even like a logistic regression, or you know, for example, you wouldn't be able to do this to calculate the parameters for like a spline, right? It's only for calculating betas in the linear form. The beauty of the numerical method is that you are able to apply that algorithm to any function. By using gradient descent, essentially what you're doing is you are doing a smart version of guessing and checking. You're looking at essentially the gradient, the derivative, right, of a function, and you're essentially going in the direction where you're improving the best way to think about it is that you're kind of like guessing and checking your betas, or in this case, your weights, in a smart way, such that every time you guess and check, you're getting closer and closer to your final solution, because you have some kind of like loss function that's giving you like a better score every time. And the other thing about the flexibility is that that scoring and that loss function that I was telling you about can also be very flexible. So if I kind of analogously think about that in terms of my linear regression, right, the thing that you are optimizing is specifically the sum of the squared value of all of your residuals, right? And that's like a perfectly fine that's a perfectly fine metric for scoring your model, but you might want to choose like a different possibly a different metric, right? And you can do that here very easily. Whereas the solution in an analytical form would have to be different if you were to choose a different scoring mechanism. So let's draw kind of a generalized diagram of this so that we can see how this kind of approach can be really flexible. So we'll have our input, and this goes to a new layer. So this has some kind of transformation to it, right? And so the transformation that we looked at in, all that means is that in the previous version, where do I have it? Over here, this equation here, this is my transformation, and it leads to this output. So that's you have a new layer starting from your inputs. So that's what we're talking about here. And so in this particular case, we only have one new sort of final output layer. But in a sort of more generalized form, I can have kind of as many layers as I want. And eventually what we want is to have some predictions about your particular outcome. And we can compare that to our true values, y. So these can go into a loss function. And there are, again, lots of different ways that this loss function could be structured, right? But one really simple one could just be like my y hat minus y. So what's the difference between my prediction and the true value? You could have this squared, right? And then that would be kind of like, that would be similar to the OLS. This could then be used to calculate your loss score. And so this might be something like your mean squared error. And this is the thing that goes into your optimizer. So this might be your gradient descent function. And we have weights that apply to our transformations. And you could have essentially the weights getting updated here. All right. Any questions about this or confusion? So this is essentially a generalized schematic of how we're going to structure our neural networks. And we'll talk a little bit more about this transformation. The example that I've shown is simply just to kind of mirror the linear regression so that we can see how a neural network can be generalized to that. But now we're going to talk about sort of non-linear transformations that make that really describe some of the power behind the neural network and its inherent sort of flexibility.
I was just wondering about the gradient descent function. So that's like an optimization technique, right? Tells us the minimum or.
Yeah, that's exactly right. So let's see. The gradient descent function, all right, I'm gonna, actually don't have this in my notes, but I'll operate off of memory here. So if anyone can correct me if I'm making a mistake. So you have x of n plus 1. I think this is the classical form of it that's that you learn about in optimization. I think it goes like this. F of xn, I believe. Yeah, that looks right. So what you're essentially doing here is like an updated iterative procedure, I guess I would need to think a little bit more carefully about, you know, the exact structure of this as it relates to our example. But the idea is, the idea is you go through this iterative stepwise procedure where, let's say I start, so our equation is, so our function was, so essentially what's going to happen is I will start with a guess about my W, my weights, right? The betas essentially. You're going to start with some kind of initial starting point. And then what you'll do is, these are actually going to be your X's here. Actually might be, okay, just to make it a little bit more analogous, we could call these W's. And obviously it's not going to be sort of directly one-to-one the same, but what you're doing is you are updating the value of your weights iteratively, and every time you go through, you are making it so that your weights are improving the mean squared error, and that has to do with going down the gradient. So if you had, so for example, let's say this is your W11 and this is your W12. And I think the best way is to draw it with different thicknesses. So we'll do this and this. So thicker lines equals higher mean squared error, and thinner lines equals lower mean squared error. So you could have some kind of shape that looks like this. And essentially what you do is, so you can kind of think of this map as like a cone going down into like a valley. So I'm going to pick an arbitrary starting point. Let's say I start right here. What the sort of qualitative way that I would describe what the gradient descent is doing is it will so this isn't actually what it's going to be doing, but you can imagine that I can look in many different directions. And if you imagine this red dot as like standing on a hill, like it will be able to see that if I go down this direction, that I'm going to be lowering my loss score the most. And that's based off of gradients and derivatives, right? So it will then take one step in that direction and say, okay, now my loss score has improved. I'm going to then iterate again for my next guess and move down like this, and then finally move down to here. And then essentially what ends up happening is you take kind of smaller and smaller steps, and you can have a cutoff value that says, okay, if the mean squared error, if the improvement in your mean squared error or in your loss score is under some delta, then you can stop and say that that's good enough, which is why you're never really getting, I would say, the exact answer compared to doing the analytical solution, particularly in this kind of you know, linear form. You know, your W's may be like super close to the betas, or they, and in a lot of cases, in a simple example like this, it'll probably match exactly. But the really benefit is that you can do this kind of thing for lots of different functional forms. Okay, so hopefully, so okay, I think Maha, you were asking this question. Does this clarify a little bit about what gradient descent is doing?
Yes, thank you.
Yep, great, great. Yeah, I should, I'll actually see if I can, next class, I'll look into the actual application of how you would apply gradient descent for this particular equation, like in that form. So I will look into that, and we could quickly show like a handwritten example of application of gradient descent for calculating a linear regression. Okay. But again, gradient descent doesn't only have to be applied to solving for these linear models. You can do it really generically, which is, again, some of the power behind this. Okay. So now let's think about how we could extend let's think about other functional forms of the model. And we've actually talked about some of this stuff before, right? So if I go back to our old notation, you know, we could also have like a logistic model, which would be, you know, 1 over 1 plus e to the negative beta x, right, is one other type of functional form that you could take for your model. And what the particular form, what the particular form of the model that we've written for neural networks can do is to actually have what's known as an activation function, which lets us transform our parameters into different functional forms. And it can generalize into things like the linear model, but also into things like the logistic model. So let's show what this looks like. So all you have to do is actually just have this A in front. So A is the activation function. Oops. function. And this allows for a nonlinear transformation of the inputs at each node. Okay, so some common activation functions. So you've got the identity / linear, and this would just be for f of x is equal to x. And so if I drew a plot of this, that would just be like a line. And that would be what we've been talking about and working with. You can have another common one is the step or binary step. And so this is f of x is equal to 0 for x is less than 0, and 1 for x is greater than or equal to 1. So this would look something like this. You would have, let me actually draw these in red. So it would look like this. You could have the logistic. So f of x is equal to 1 divided by 1 plus e to the negative x. This will look something like this. So 0 and 1. And so you can see how this form as your activation function would allow you to treat these weights in such a way that would essentially be your logistic function, right? So that in this particular example, it would be F2, I1, I2 from above. Instead of writing the activation function, it would be this equivalent to writing it explicitly. So 1 plus e to the negative, W11 I1 plus W12 I2. And then two more that I think are very commonly used. We've got tan h. So this is f of x is equal to e to the x minus e to the negative x divided by e to the x plus e to the negative x. And this is kind of similar to the logistic, actually, except instead of going from 0 to 1, it goes from -1 to 1. And the last one, rectified linear unit. which I believe is one of the most common ones. ReLU, and this is 0 for x is less than or equal to 0, and x for x is greater than 0. And this looks something like this. 0, 0. Okay. Why don't we take a quick break here for 5 minutes, and then we'll move forward and talk about how we can add in layers and how that allows us to do a specific type, or how that allows us to build a specific type of neural network. So let's do 5 minutes. And in the meantime, if anyone has any questions, I'm happy to answer.
Hi, Alan.
Hello.
Hello. I have actually a quick question. What's the difference between the stochastic gradient descent and the gradient descent when we use this stochastic gradient descent?
Yeah, so I don't know the exact like application for it. Usually I leave it up to the built-in solvers, but the stochastic gradient descent is just a specific type of algorithm in gradient descent. There's actually a whole bunch of gradient descent algorithms that you can use. Let's see. I don't know if I know the algorithm off the top of my head. But yeah, it's simply one of the common types of gradient descent algorithms.
Thank you.
Let me see. I see. Okay, so I guess you could generalize it as a batch. There's batch gradient descent and stochastic gradient descent. Batch gradient descent calculates the gradients for all of the parameters in the entire data set, whereas stochastic gradient descent does updates one parameter at a time. So I don't actually know which one's better, but it seems like stochastic gradient descent would be faster. Well, maybe. But with batch gradient descent, you're going to have like redundant calculations in your updates, because if, for example, you can update the parameter value in a smart way with stochastic gradient descent, you could bypass values that you would find in the batch gradient descent. That's why I think it might be faster, but it may be context dependent on the problem. Yeah.
Thank you.
Alrighty. So let's continue on, unless there are any other questions. So we're going to talk about what's known as a feed-forward neural network. So this is also known as a multi-layer perceptron. Okay, so before we had our I1 and our I2, our inputs, feeding directly into the output with a single linear transformation as the first example, or a single transformation with some kind of arbitrary activation function in our second example. So let's say our outcome that we care about is P. And instead now what I'm going to do is I'm going to insert an in-between layer here, so that we're going to actually do two sets of transformations before I get to my output. So now I'll have something that looks like this. And then here. So this is kind of like a classic example of a type of diagram that you would see for these kind of neural network examples. And it's kind of exactly the same as we have before in terms of thinking about the transformation. So this is going to be each one of these arrows connecting the nodes is going to have some kind of weight associated with it. So W11, we'll say W21, and this one will be W31. And then the other sets of lines will have W12, W22, and W32. And then we'll have a different set of weights here. We're going to call them V1, V2, and V3. So we'll go through these one at a time. L1 is going to be equal to, we're going to have some kind of activation function, and it's just going to be W11 and W12, right? So W11 I1 plus W12 I2. And then layer 2 is going to have a different activation function. We'll say 1, 2. And those are going to be based off of the weights going in there. So we'll have W21, W22, and that's going to be I1 and I2. Layer 3, same deal. We'll have an activation function, and then it's going to have two sets of inputs, W31, W32, like so. And for our P, we will have another equation. P is equal to activation function with, well, let's say each of our weights here. So V1, V2, V3. And that's going to be, oops, L1, not L2. L1 plus V2 times L2 plus V3 times L3, like so. And you can imagine now that you're doing essentially this transformation using whatever activation function. Let's say you're doing like a logistic transformation, and then you're going to do that again. And by having both the activation function, and you can see this kind of like plethora of parameters, all of these things are introducing flexibility in how you get from your I's to your P's, from your X's to your Y's, essentially. So this is known as a hidden layer. All of your sort of first transformation, and all the layers that are in between your input and your final output are known as hidden layers. And what you can see here is that we can introduce flexibility, right, by adding more hidden layers and or adding more or less nodes within each of the hidden layers. So in this particular example, we have one hidden layer, and within that hidden layer, there are three nodes. They're also called perceptrons, which is why this is a multi-layer perceptron. So then the question becomes, how many hidden layers and nodes / perceptrons to include in the feed forward neural network. And this is, again, kind of related to the questions we've been having before about essentially how much flexibility do we add into the model. And in this case, it's a little bit more complex, right? We usually think about doing this in the context of like a cross-validation in order to select, but we have kind of multiple degrees here. But what I can say is that generally, so okay, for a number of hidden layers, generally 0, so this represents linearly separable functions. And that makes sense, right? The functional form is, you know, your weights times your input values. And that may go through some kind of transformation procedure, but it's all linearly separable. If you have one hidden layer, this will approximate any continuous mapping in finite space. And that's why very often you see models that will just have a single hidden layer, because doing this double transformation lets you map basically anything in finite space. 2 plus represents arbitrary decision boundaries. To arbitrary accuracy. With correct activation function. Yeah, and so this will allow you to map to like discontinuous functions, because with multiple of these layers, it doesn't even necessarily have to be continuous. So no, I would say there's not really an agreed upon method, but rules of thumb. To keep in mind. Size of input layer. Usually is going to be bigger than hidden nodes, bigger than size of output. And this is kind of like a dimension reduction type of thing. Some people think about hidden nodes, approximately 2/3 input plus output layer size. Hidden nodes less than 2x input. And also Yeah, so these are all different kind of examples that or common examples that I've seen for number of nodes. Where alpha is somewhere between 2 and 10. Generally, the more nodes that you have, the more prone your model will be to overfitting. So that's one thing to keep in mind. All right. Any questions?
I have a quick question.
Yep.
So the hidden nodes are like the L1 through 3 in the previous.
Yeah.
Thing. So that's
over here.
So ideally, we'd want to have like there'd be fewer nodes than eyes.
Yeah. Well. Yes and no. I would say it wouldn't be unusual for something like this. I would say it's more applicable for if you have like a crazy amount of nodes, which is or if you have a really, really large number of features, usually you go down in dimensions. But when you don't have so many, as long as it's close, I think it's generally okay. So like this particular example, going from 2 up to 3, might be slightly unusual, but not too crazy. But I'm usually thinking about this in terms of applications where you may have like 1,000 inputs, and usually you wouldn't go up in the number of nodes in the hidden layer. Yeah.
Oh, okay, that makes sense.
It's all about kind of introducing like degrees of freedom.
I have another quick question. So when we're talking about the number of nodes in the hidden layer, we're talking about it for a single layer, right?
Yep, that's right.
So, and the number of them are like when we decide what number is proper, they're all mainly dependent on the input and output instead of like relative input and output, like the layers, maybe the hidden layers that is nearby.
So yeah, okay. I think if I'm interpreting your question correctly, like you're saying that the selection of the number of nodes within the hidden layer is more dependent on the number of nodes in the inputs and outputs rather than the neighboring hidden layers.
Yeah, exactly.
Yeah, I think that's generally right. Although, again, I think that kind of question applies more specifically to like if you have 2 or more hidden layers, right? And in those cases, I think that those cases in general are going to be less common, but yes, I think the rules in general are meant to be applied to, yeah, thinking about the relative numbers in your input and output layers.
Okay, got it. Thank you.
Yeah. Okay. Great. So let's hop on over to our studio and let's see if we can apply this in R. I'm going to load in data from ISLR. We'll just load in a couple other packages as well. Okay. So I'm going to look at a data set called defaults. Let's have a quick look at this.
I think it's frozen.
Oh no, okay, great. Here we go again. Stop sharing and we'll try it again. Of course, wait 10 minutes for this. Okay, but if you do data parentheses defaults, that will load in defaults and we can take a look at it. So even as this loads, I'll just kind of verbally describe the data set. It's 10,000 observations and there's 4 variables. You have default, student, balance, and income. So the variables default and student are both binary variables. So default is yes or no, and student is yes or no. And then both balance and income are continuous. So what we'll be doing here is we will be trying to do a prediction and see whether or not we can predict if the information of being a student and then having a specific balance in income is going to be enough for us to accurately predict whether or not that particular data point or person is in default. So we'll wait for this to load, and I'm actually going to go ahead and continue typing some code here. All I'm doing is I'm going to change the binary variable that I was talking about. You have your default and student. I'm just going to change it from yes and no to ones and zeros. And so whenever this comes up, we can quickly go over and review how I was doing that. If it doesn't come up soon, then I will simply copy and paste it into chat. Oh, there we go. Okay, so as I was mentioning, I'll just quickly go over this. In the table, 4 variables, and you can see which ones are binary and which ones are continuous. I made it into a data table so that I could do this. So all this is I am assigning a column called default, and it's actually an existing column, so it's going to replace the values. And what all it's doing is so I use an if-else statement, which is the same as like an if statement in like Excel. It's the condition that it checks. So does default equal yes? And if it does, I'm going to change it to a 1. And if it's not yes, it's going to be a 0. So that's all we're doing here. And if I go back to my table, I can now see all the zeros. Yeah. So ones are appearing for any time they're defaulting or if they are students. Assume there's some students in this data set. Maybe not. Actually, we can take a quick look. If I do summary, default. Oh, there are actually no students?
I think there's.
Okay, I did. My bad. There should be students. Okay, so we need to redo this. Good thing I checked. There we go. There's a couple. Yep. In this case, I'm actually going to scale it. Okay, in the scaling that we've done before, this allows, when we've done scaling, it's been for things like k-nearest neighbors, for example, where it's concerned with distances. The scaling in this case is actually more to help with the efficiency of the gradient descent algorithm. You can imagine that if I have, if you remember that mapping where I have W11 and W12, if those values are really different, you know, if for one of the weights, it's working on the thousands or millions scale, and on the other weight, it's working in the 0.1, 0.01 scale, the tenths or hundredths or something, that affects the direction of the step that you walk in the gradient descent, right? And so in some cases, it can be, or it's very often suggested to do some kind of scaling to essentially help with the numerical optimization portion. So that is what we're going to do. And in this particular case, I'm also I don't need to scale the y, the response variable. So what I'm doing is I'm just creating I'm creating a sort, and I'm sampling from it so that I'm going to be creating a training set and a testing set. And the training set will contain 70% of the data that I pick at random. So that's going to be default.train. It's going to include all the row indices from default sort. And then our testing set is going to be everything besides those. So I have a minus there to do that. So I will go ahead and run these lines of code. And we can see testing and training. We've separated our 10,000 observations into here. And if I look at these compared to default, which is here, so look at the size of the balance and income, you'll notice that they're all slightly different now. because everything's been scaled.
I have a quick question. Could you explain what the student scaling did? So it already was between 0 and 1, right?
Yes, it's scaled everything relative to each other, so the zeros end up getting, you know, negative 0.64, and then the ones end up getting 1.54. So they're all like relative to each other, maintaining some kind of set distance. In this particular case, we're kind of treating, and this is where there's some kind of important distinction between a lot of the inferential methods. We're kind of treating the student variable or feature as a continuous object. But in this case, like when we think about doing that in the context of like a linear regression, you would turn it into like a dummy, and then it'd be like a 1 or 0, because we want to have some meaning to the beta. In this case, it looks weird when you do the scaling, but it still retains the information that there's like a specific difference between being a student and not being a student. And then we don't like care about the inference so much. And so as long as we pass the information that there's this distinction, it's generally fine, because you are still, you still pass that necessary information into the model to do the prediction. And so when I do like a test set against that model, like it doesn't necessarily care that it's 0, 1. It's just like, as long as it takes this one particular value, I want to be able to give a good prediction off of it, if that makes sense. So it's a little bit weird when you think about it from an inference perspective, but you don't really care that you have this weird negative 0.64 value or 1.5 value when you're just thinking about it in terms of prediction.
Okay, that makes sense.
Yeah. So we're going to use a package called neural nets. So again, this won't be a default one. So if you are following along, you'll want to quickly run this once to install the package. So this model is going to be our, so looking at the defaults, neural network. So we're going to do a neural net. And it's just going to be default measured against everything else. So we're going to use default.train as our training model. And then there is an input parameter called hidden, which lets you specify both the number of layers and the number of nodes within each layer. And so I'm just going to be kind of arbitrary here. I'm just going to do something like this, which means there's going to be 2 layers. The first layer is going to have two hidden nodes, and then the second layer, the second hidden layer, will have 3 nodes. And again, you know, if this were like a more sort of realistic example, if I had like 1,000 features, I might choose something like, you know, 750 with a single layer if it's a continuous mapping, or I might have 2 layers and then split up those nodes. Oh, okay. So ACT.FCT, this stands for activation function. I'm going to have it as a logistic because it's a binary output, and so linear output will be false.
I have another quick question. Sorry.
Yep.
Do we need multiple hidden layers because the output is a discrete variable, or
no,
would one layer?
No. So you could have, so okay, the output will just be whatever sort of output it is. You could have, so let me do this, and then let's take a look at this question that you're asking in particular and see if it works, right? So I will run this. And it's gonna take a second to run. It's going through the gradient descent procedure. And then when you just plot that model, it gives you this thing. So this contains all the information you need about your weights here. It tells you the size of your error, and we can, this error report is gonna be your, I believe this should be the mean squared error. And then steps is the number of iterations in the gradient descent. Each of the values associated with the arrows are going to be your respective weights. So we could actually go in and given each of these numbers, we could sort of like manually, calculate the values that you would get through this neural network to get your final default. So again, in this particular case, our input layers, we have our student, balance, and income. And then like, we probably have too many nodes here, but this would be your first hidden layer having 2 nodes, and then your second hidden layer having 3 nodes. You could do, I think, something like this. Let's say we just wanted 2. I think this should work. In which case you should have 1 hidden layer with 2 nodes. Oh, yep, there we go. I don't know why it popped in a different window. But it will look like this. And then, so in this particular case, you don't need to have 2 layers. And in fact, if I were to, I wonder, I'm not sure if this will work. But the idea here is that this, if I had no hidden layer and I just had it as a logistic, this should, in theory, give the same results, the same weights as a logistic regression. And in fact, maybe we could run that and see if it does indeed give us the same answer. See, it should be data equals default.train. And trying to remember if someone can help me with this. Is it method equals binary?
Family?
Oh, family is equal to binary. That's right.
Binomial, I think. I don't know.
Oh yeah. Binomials. Yeah. So let's see. Okay. Summary default. Is it gonna make me eat my words? Nope. That's right. Yeah. So we got pretty close values. In this case, this doesn't have an intercept. Actually, I wonder. I don't know if it works in GLM, but let's take a look. I think it does. Yep. So if we take out the intercepts, it'll look like this: 0.28, oh, the balance is actually pretty different, isn't it? Or everything is scaled by 10. It's not going to be exactly the same, but it's going to be pretty darn close. And again, that's having to do with the estimation procedure. And this, the GLM is going to be actually solving using maximum likelihood estimation. Neural networks is doing the gradient descents. And so you're not always going to get the exact same, but this is going to be very similar. And in fact, we can look at the predictions, the predictive ability of these by using something called compute, which is like predict. And we can use the test set here. And I can add
I think the intercept is like the bias value, yes?
Yeah. Oh yeah. In the activation function.
Yeah.
Yeah. Oh, that's why. Yeah. So I should include the intercept then, because that's like that makes sense, because you have your epsilon value, which is substituting essentially for the intercept. So actually, if I don't include it, then it looks very similar. A lot closer, I guess. Or don't include the 0, which means to include the intercept. Yeah, so it looks like this. So we'll do that. Yep, you're right. This lets you get very close. Okay, where was I? Oh yeah, okay. So what we're gonna do now is we're gonna test the out of sample predictive ability of our neural network. So I use this compute function, and if I take a look at this, it's gonna give you a whole bunch of information. In this particular one, these are each of my predicted probability values. So you have two outputs. So the net results are the probability values, and then the neurons. These are the predictions for each of your neurons. In this case, we don't actually have hidden layers to look at, so it's not quite as interesting. So all I'm going to do is add a new column to my test set called probability, which is assigned as those predicted values. Why isn't it showing up here? Here we go. I had to update it. So given a specific input, it's going to have my output probability coming as a prediction out of my neural network. And then we can create a prediction where I'm going to say, okay, if the probability is greater than 0.5, then we'll say 1, otherwise we'll say 0. So this is going to, if I reopen this, this is the model predicting whether or not it's any one particular outcome defaults. And so you can see, oh, did it get it right? It did not in this case. And we can look at that overall. So the overall mean squared error would be sum of the default test $default. So this is your out of sample predict squared divided by n row default test. Oops. So that is our mean squared error value. False negative rates. This is how often it says I don't default, but you actually do. And you'll also have a false positive rate, which is how often it says you default, but you actually don't. So that would be how often it's greater than the prediction. Then we'll give it 1 or 0 divided by n row default test. And this is if it's less than. Okay. So because there are many more incidents of not defaulting than there are defaulting, the portion of your mean squared error that is coming from false negatives is going to be a lot higher than the proportion of your errors coming from your false positive. And when we do the gradient descent function, this might be one of the areas where you could like modify your loss function, particularly if you care about if you care more about like your false negative rate versus your false positive rate. Instead of calibrating your model to the overall mean squared error, you could actually calibrate the model to have like a a better false positive rate. And what that could do is that could actually raise your overall mean squared error, but then you could get less instances where you say someone's defaulting, but they're not actually defaulting. And so again, this is one of the nice things about these neural networks is the really sort of generalizability in not only the functional form, but also in the loss function to actually calibrate your weights. And actually the last thing that I want to do, let me go back to the first hidden one, and let's kind of recalculate this. And I'm just kind of curious to see whether or not the you know, as we add more layers and as we add more flexibility, are we getting to the point where we're doing overfitting, in which case our out of sample overall mean squared error would tend to be higher, or is it still kind of improving? So I'll run this, and then while this kind of runs, you know, one thing that I might note for everyone is that like you could go in and do a lot of the like model comparison stuff as I just did here. You could even see whether or not a simple logistic regression is going to be doing a lot better or a lot worse than these neural networks, depending on how you structure them in terms of hidden layers and number of nodes. Okay, so this is still going. Again, this is probably really inefficient because you're introducing more degrees of freedom with the 5 nodes compared to your 3 inputs. You're introducing more degrees of freedom, and that might be kind of making the function really flexible, so the gradient descent is going to take a much longer time to find a good answer. In some cases, so this is more kind of a general discussion about optimizations in general. That drawing that I made with like a cone and sort of moving down that gradient, you could imagine that in really nonlinear topologies, you could have multiple like bowls essentially. And so you could be going down your gradient descent and you could get trapped at the bottom of a bowl where you might have a better one somewhere else. And so the way that some of these gradient descent algorithms will work is that in order to partially alleviate that issue is they'll start at many different places so that you could go down like different bowls, if that makes sense, to try and find the lowest one. We seem to be getting stuck here for some reason. Let me actually I'm going to stop this and let's just try it with 2 so that we're actually following our rule. We're kind of reducing the number of nodes. Hopefully this will be faster. There we go. And so just as a reminder, so I'm going to clear this and let's plot it really quick. So that's what this model looks like, where we have 1 hidden layer with 2 nodes. And let's look at the error rates. Yeah, in this case, it's actually getting the same number, correct in terms of the errors. The other reason why you might care about these a lot more, and you can think about how to structure this, is that you may have a really small number of defaults, which I believe is the case here. Summary defaults. Um, 0.0333. So if I made a model that guessed all of them as 0, then my error would just be 0.0333, which means that this is only getting, really, it's only getting like 2/3 of those correct, right? Out of the, if I were to compare against the ones where you really just care about the default, right? You're being compared to a standard where it's your error rate is just equal to the actual number of observations there are, is actually a pretty good indication that the model is probably in itself just not all that good. So that's one thing to keep in mind when your outcomes are really unbalanced in that case. I hope that like makes sense to everyone, right? So like the fact that you have this like a small number of defaults by sort of by corollary kind of makes it so that your error rate in itself is going to be really low, because you potentially, if you just guessed all of these as 0, like you're not going to get a bigger error rate than this. So sometimes you can, depending on the structure of your problem, compare your error in that way. In which case I might say that like, if I look at my false negative rate compared to this, well, I'm actually getting half of the predictions wrong, right? More than half of the predictions wrong, because 0.018 divided by 0.033, that's like larger than 50%. So it's not a great track record for the model, I would say. Okay, so I think we will wrap it up here for today. Yeah, and that'll be it for the course material. In terms of logistics, the last homework has been posted. I think this one's going to be a little bit easier, a little bit shorter. So that will give you guys more time to work on the projects. For the notes that I've been posting, I'm a little bit behind again, but actually those will be done for sure by the end of the week for all the lectures. So those will be getting posted to Canvas as soon as possible. And then lastly, I kind of have a loose kind of schedule for the next couple lectures. So if folks have like specific preferences, if you'd rather sort of continue on looking at some of the machine learning material, that's totally fine. But there's also an option we can do a sort of deeper dive into the material on R to do like data parsing and summary and graphing. We can get a little bit more into detail on that if folks are interested. yeah, or we can continue on with this sort of material. So if anyone has any preference, you can let me know. And also if there are any folks who want to review any material, I'm happy to do that as well over the next couple lectures. So we'll end here for today, and I will see everybody on Wednesday. And of course, I'll stick around a couple minutes if there are any questions on anything related to the class.